Do you think, because you're also a fan of theoretical computer science and complexity, do you think we can come up with a kind of complexity class, like a complexity zoo type of class, where maybe it's the set of learnable systems, the set of learnable natural systems, LNS?
Yeah.
This is a Demis
A new class.
Hassabis new class of systems that could be actually learnable by classical systems in this kind of way, natural systems that can be modeled efficiently.
Yeah. I mean, I've always been fascinated by the P equals MP question and what is modelable by classical systems, i.e. non-quantum systems, Turing machines in effect. And that's exactly what I'm working on actually in kind of my few moments of spare time with a few colleagues about should there be, maybe a new class of problem that is solvable by this type of neural network process and kind of mapped onto these natural systems. So, the things that exist in physics and have structure. So I think that could be a very interesting new way of thinking about it. And it sort of fits with the way I think about physics in general, which is that, I think information is primary. Information is the most sort of fundamental unit of the universe, more fundamental than energy and matter. I think they can all be converted into each other. But I think of the universe as a kind of informational system.
So when you think of the universe as an informational system, then the P equals NP question is a physics question.
That's right.
And it's a question that can help us actually solve the entirety of this whole thing going on.
Yeah, I think it's one of the most fundamental questions, actually, if you think of physics as informational. And the answer to that, I think, is going to be, very enlightening.
More specific to the P and NP question, this, again, some of the stuff we're saying is kind of crazy right now. Just like the Christian Anfinsen Nobel Prize speech, controversial thing that he said sounded crazy, and then you went and got a Nobel Prize for this with John Jumper, solved the problem. So let me just stick to the P equals NP. Do you think there's something in this thing we're talking about that could be shown if you can do something like polynomial time or constant time compute ahead of time and construct this gigantic model, then you can solve some of these extremely difficult problems in a theoretical computer science kind of way?
Yeah, I think that there are actually a huge class of problems that could be couched in this way, the way we did AlphaGo and the way we did AlphaFold, where you model what the dynamics of the system is, the properties of that system, the environment that you're trying to understand, and then that makes the search for the solution or the prediction of the next step efficient, basically polynomial time. So tractable by a classical system, which a neural network is. It runs on normal computers, right? Classical computers, Turing machines in effect. And I think it's one of the most interesting questions there is how far can that paradigm go? I think we've proven, and the AI community in general, that classical systems, Turing machines, can go a lot further than we previously thought. They can do things like model the structures of proteins and play Go to better than world champion level. And, a lot of people would have thought maybe 10, 20 years ago that was decades away, or maybe you would need some sort of quantum machines to quantum systems to be able to do things like protein folding. And so I think we haven't really even sort of scratched the surface yet of what classical systems, so-called, could do. And of course, AGI being built on a neural network system on top of a neural network system on top of a classical computer would be the ultimate expression of that. And I think the limit, what the bounds of that kind of system, what it can do, it's a very interesting question and directly speaks to the P equals MP question.
What do you think, again, hypothetical, might be outside of this? Maybe emergent phenomena? Like if you look at cellular automata, you have extremely simple systems and then some complexity emerges.
Yes.
Maybe that would be outside, or even, would you guess even that might be amenable to efficient modeling by a classical machine?
Yeah, I think those systems would be right on the boundary, right? So I think most emergent systems, cellular automata, things like that, could be modelable by a classical system. You just sort of do a forward simulation of it and it'd probably be efficient enough. Of course, there's the question of things like chaotic systems where the initial conditions really matter and then you get to some, uncorrelated end state. Now, those could be difficult to model. So I think these are kind of the open questions. But I think when you step back and look at what we've done with the systems and the problems that we we've solved. And then you look at things like VO3 on like video generation, sort of rendering physics and lighting and things like that, really core fundamental things in physics. It's pretty interesting. I think it's telling us something quite fundamental about how the universe is structured, in my opinion. So, in a way, that's what I want to build AGI for, is to help us as scientists answer these questions like P equals MP.
Yeah, I think we might be continuously surprised about what is modelable by classical computers. I mean, AlphaFold 3 on the interaction side is surprising that you can make any kind of progress on that direction. Alpha Genome is surprising that you can map the genetic code to the function. Kind of playing with the emergent kind of phenomena. You think there's so many combinatorial options and then here you go. You can find the kernel that is efficiently modelable.
Yes, because there's some structure, there's some landscape, in the energy landscape or whatever it is that you can follow, some gradient you can follow. And of course, what neural networks are very good at is following gradients. And so if there's one to follow and you can specify the objective function correctly, you don't have to deal with all that complexity, which I think is how we maybe have naively thought about it for decades, those problems. If you just enumerate all the possibilities, it looks totally intractable. And there's many, many problems like that. And then you think, well, it's like 10 to the 300 possible protein structures, it's 10 to the 170 possible go positions. All of these are way more than atoms in the universe. So how could one possibly find the right solution or predict the next step? But it turns out that it is possible. And of course, reality in nature does do it, right? Proteins do fold. So that gives you confidence that there must be, if we understood how physics was doing that, in a sense, and we could mimic that process, i.e. model that process, it should be possible on our classical systems is basically what the conjecture is about.
And of course, there's nonlinear dynamical systems, highly nonlinear dynamical systems, everything involving fluid.
Yes, right.
I recently had a conversation with Terence Tao, who mathematically it contends with a very difficult aspect of systems that have some singularities in them that break the mathematics. And it's just hard for us humans to make any kind of clean predictions about highly nonlinear dynamical systems. But again, to your point, we might be very surprised what classical learning systems might be able to do about even fluid.
Yes, exactly. I mean, fluid dynamics, Navier-Stokes equations, these are traditionally thought of as very, very difficult, intractable kind of problems to do on classical systems. They take enormous amounts of compute, weather prediction systems, these kind of things all involve fluid dynamics calculations. And but again, if you look at something like VO, our video generation model, it can model liquids quite well, surprisingly well, and materials, specular lighting. I love the ones where, there's people who generate videos where there's like clear liquids going through hydraulic presses and then being squeezed out. I used to write physics engines and graphics engines in my early days in gaming, and I know it's just so painstakingly hard to build programs that can do that. And yet somehow these systems are, reverse engineering from just watching YouTube videos. So presumably what's happening is it's extracting some underlying structure around how these materials behave. So perhaps there is some kind of lower dimensional manifold that can be learned if we actually fully understood what's going on under the hood. That's maybe true of most of reality.
Yeah, I've been continuously, precisely by this aspect of VO3. I think a lot of people highlight different aspects, including the comedic and the meme and all that kind of stuff. And then the ultra realistic ability to capture humans in a really nice way that's compelling and feels close to reality, and then combine that with native audio. All of those are marvelous things about VO3, but exactly the thing you're mentioning, which is the physics.
Yeah.
It's not perfect, but it's pretty damn good. And then the really interesting scientific question is, what is it understanding about our world in order to be able to do that? Because of the cynical take with diffusion models, there's no way it understands anything. But it seems, I don't think you can generate that kind of video without understanding. And then our own philosophical notion of what it means to understand then is like brought to the surface.